In this episode, let's take a look at a method of growing large, flawless crystals of potassium dihydrogen phosphate like this in just a few days. In a previous video, I grew potassium dihydrogen phosphate to be used as a frequency doubler in a laser. This was grown by the traditional slow evaporation method, where the crystal is hung from a piece of fishing line in the salt solution and left until the crystal grows large enough to be useful. To grow this particular crystal, I had to wait around 6 weeks, and as we can see, it is far from perfect and really quite small. Potassium dihydrogen phosphate is a material with truly remarkable properties. It's piezoelectric, generating electricity under compression, has a high nonlinear optical effect that can be used for changing the wavelength of laser light, a strong electro-optic effect that can be used for modulating laser light, and it's even possible to use it for quantum entanglement experiments. For these applications, the crystals need to be completely free of flaws and grown large enough to be cut. As a consequence, these things can be incredibly expensive to buy. Some crystals can be very easy to grow and will grow really quite fast. For example, alum and copper sulfate. These are both hydrated salts, and so water becomes part of the crystal lattice, contributing to volume. Other salts, like KDP crystals, can be difficult to grow perfectly using evaporation and grow very slowly, and so changes in relative humidity, temperature, dust and other issues conspire over time to ruin a crystal. The fact that the crystal is just statically sitting there in solution also causes problems, especially if we try and grow it quickly. If we imagine a crystal hanging by a thread in solution, as the water slowly evaporates, more molecules become deposited on the surface, and there's always molecules available to become part of the lattice because Brownian motion is moving them around quite rapidly. If somehow we could speed up the growth itself, for example by starting with a hot solution, we might end up with a situation where the solution in the immediate vicinity of the crystal is actually depleted, which stalls growing. The depleted solution, being less dense than the surrounding solution, becomes buoyant, rising to the top and dragging concentrated solution with it. This causes rapid variations in the concentration at the surface of the crystal and can cause slowing growth rates and defects. There is a more precise way to grow crystals, and that's to use a controlled slow cooling method. I've got a very nice book here on this subject called Growing Crystals with a Rotary Crystallizer, and it was published by Alan Holden and Robert Thompson by Bell Telephone Laboratories. The book describes in great detail the slow cooling method, and what we do is we start off with a hot solution and then gradually lower the temperature over a number of days. The cooling rate described in the book is 0.1 to 0.2 degrees per day. So while we grow crystals really quite slowly, we have really fine control over how we grow the crystal. In order to produce favorable hydrodynamic conditions for crystal growth, the book describes a rotary crystallizer. On the right hand side here we have an overall view of the rotary crystallizer. At the top we have a simple glass tank that will contain the supersaturated solution, and then we have a motor and a shaft. On the end of the shaft are 4 pegs, and these pegs are where we would mount the crystals. The idea behind the motorized assembly is that as the motor turns, it will ensure that the solution is thoroughly mixed, it will ensure it's homogeneous, and it will also drive seed crystals through the solution while they grow. To keep this set up at a fixed temperature, what we actually have is a spot lamp down at the bottom to heat up the solution and a thermal regulator at the top. The thermal regulator itself is really quite interesting. Internally it's a mercury thermometer that has a wire dipped into it, and the idea is that if the solution is cool, then there'll be a gap between the mercury and the wire, breaking the circuit, and if the solution is hot, then it'll drive the mercury up the column to make contact with the wire. Really quite fascinating. According to the book, the thermal regulation that's actually achieved by this system is really quite good, something like 0.1 degrees. There's a little schematic on the next page here that shows how this system all fits together. So we've got the thermal regulator driving a relay which drives the lamp, and that's pretty much all there is to it. The rest of the book's excellent, with some really fantastic hints and tips all the way through it. There's even a section here on how to harvest the crystals themselves without cracking them. There's been a huge amount of research on growing potassium dihydrogen phosphate quickly. This has been motivated by the need for huge optics for the National Ignition Facility. The abstract really gives away what this entire paper is about, which is pretty good. It says the rapid growth of KDP crystals was demonstrated at growth rates of up to 54 millimeters per day. Thermal and acoustic energy were used in the saturated solution to delete clusters of molecules. High supersaturations larger than 120% were achieved by overheating the mother solution by 25 Kelvin. The application of acoustic energy to the solution was also used to achieve high supersaturation. So we'll just scroll down the paper real quick and take a look at the main points. We've got an introduction here which describes the motivation behind this, which, as I've said before, is nuclear fusion experiments where they need really large optics up to 400 millimeters in diameter. If we were to grow KDP by evaporation, we might be waiting a very long time, on the order of years, to grow a suitably sized crystal. So further down the paper here, there is a discussion on rapid growth. This is quite a long, wordy section, so I'll just summarize it real quick. In short, if I calculate how much salt it takes to dissolve in a given solution and I mix that salt in and stir it up and heat it a little bit, eventually it will appear that all of the crystals have dissolved and we'll end up with a crystal clear solution. But it turns out it only appears that way. It turns out that within that solution are microclusters of crystals on nanometer scales, so like maybe 100, 200 nanometers or so. We can't actually see those things or filter them out, but they're all there. And what this means is, if I come along and try and grow crystals in that solution, we've got a very unstable solution with microscopic crystals floating around which acts as seeds. And essentially what happens is we'll cool it down to a certain point, and then the whole thing will turn into a snow globe. It'll all just precipitate out. There's a couple of ways of dealing with these microclusters, one of which, the simplest way, is overheating. What we actually do is we cook the solution at 20 degrees above its crystallization point for a few days. The shortest time period I've seen in here is 24 hours, which would appear to be enough from all of the academic papers I've read, but some people will cook these things for like 76 hours or so. The second way that the authors have dealt with microclusters here is applying acoustic energy. So essentially we mount a transducer on the side of the container for the solution and drive it at 25 kilohertz with acoustic waves, which will help to break up any microclusters as well. I think for what I want to do, acoustic energy is maybe a step of complexity too far, but overheating is something that anybody could do. Just cook the solution for a day. Another thing that was done in this academic paper to get these excellent results was to adjust the pH of the solution. So as you lower the pH, we end up with a more stable solution. So we can see here that they've added phosphoric acid to lower the pH to about 3.2. And so with 25 kelvins of overheating, we end up with a supersaturation level of 150%, which is very impressive. You know, all of this stuff is taken together with the acoustic energy and so on and so forth. The big problem in the UK is we can no longer buy acids off the shelf, which is rather unfortunate, so acids are out as well. There's another academic paper here that describes a smaller scale crystallizer. I say small scale, it's 5 litres capacity, but they could grow really quite impressively sized crystals in about 3 days. If we scoot down the rest of the paper, we can see that the same tricks are being used in here, namely overheating the solution. Additionally, when they've made up their hot solution to begin with, they filter it through a 0.2 micron filter to get rid of any dust and grot that might be in the crystal solution. We've got a very nice diagram here of what appears to be a Holden crystallizer, just like in the book. So we have a rotating stage with the crystal mounted on it in the solution. This is put inside a very large water bath that's heated and stirred and controlled by means of a thermostat. Figure 5 has some excellent pictures of some really nice looking crystals there. Absolutely fantastic. There's another academic paper here on fast growth where they used additives in the solution, specifically EDTA. EDTA is a chelation agent which will actually mop up any heavy metal ions that are present in solution. This is really quite important, since if any heavy metal ions become part of the crystal lattice, they'll disrupt it and maybe cause things like cracking and fracturing, which is very bad in fast crystal growth. There is a 119-page document here on the rapid growth of KDP that contains every little piece of information you would ever want to know about growing these. We've got diagrams, we've got the supersaturation graph, we've got seed mounting, causes of failures, and all sorts of really useful pieces of information in here. In summary, fast growth is possible with slow cooling technique so long as the following conditions are met. We need to overheat the solution for at least 24 hours to attain high levels of supersaturation. We need to have the crystal rotate in the crystallizer at a rate favorable for crystal growth. We need to determine by experiment what the optimal cooling rate for the setup actually is. And additives like EDTA may well improve crystal quality. For my purposes, I want to build a system that's as simple as possible, built from common off-the-shelf parts using straightforward procedures, but still capable of growing crystals fast. Last November, I set out to build my own rotary crystallizer, but greatly simplified using common off-the-shelf materials that can be easily replicated by a small lab or an amateur at home. This is the culmination of a year's research and refinement. The outer case for this machine is made from a half server case that I picked up off eBay. The machine really needs to be cased up to reduce dust contamination and to help keep the temperature of the apparatus stable. So if someone opens a door, for example, it won't immediately cause a temperature change of the crystallizer, and this server case seemed to be ideal for the job and looks really nice as well. The container is nothing more than a 500ml borosilicate lab beaker. I've laser cut a couple of lids for these. The first is a simple lid with a hole for the temperature sensor, and O-rings are included to prevent the ingress of dust and limit the evaporation of water. They don't seal perfectly as beakers are not precision manufactured, and no provision has been made for the beaker spout. That gap is simply taped over with Kapton tape when the machine's running. I've drilled a divot in the middle of the lid here. The hot plate actually has a mount for a thermometer at the back, and I've built a small add-on that mates with the divot to stop the container from being able to move. This thing will be run for days at a time, and although vibrations are minimal, it might be enough to walk the container off the hot plate over a period of days. This cover was laser cut on a CO2 laser I repaired previously, and the files for this are all available on GitHub, link in the description down below. Here's the platform I've designed to hold the seed crystal and provide the necessary rotation. This assembly is directly driven by a stepper motor mounted on the lid. The platform is made entirely from perspex and bolted together with nylon bolts. No metal should be in contact with the solution, as ions can leach out. The platform itself is laser cut, and the light burn files are available on GitHub. The supports are made from 10mm perspex round bar stock. In the centre of the platform is a shallow hollow that's been milled out on the lathe. This is where the seed crystal is mounted. It's really important that all the sharp edges of the perspex are rounded off when you laser cut these, else you create unwanted nucleation sites for crystals. I hand file all of the edges of these and then polish them with Polywatch. The heater comprises of a simple laboratory hot plate that's fixed to the bottom of the case with 2-angle aluminium rails and clamps. The hot plate itself was very inexpensive and has a magnetic stirrer, which is important during the crystal growing process. The quality is very reasonable, and the thing's been used on and off for about 12 months now, running for days or weeks at a time with no issues. Tucked away in the back of the case there is a solid state relay that I use to control the heater. For temperature sensing, I use the common DS18B20 temperature sensor. This has a resolution of 0.0625 degrees, which is just good enough for this application, and they're widely available. Far better would have been a TMP117, but I haven't found a suitably reliable or common source of waterproof versions of these, but I have designed my own for future work. The sensor is pushed into the hole in the lid of the crystallizer, and this section of perspex is reamed out so the sensor fits snugly and is as deep as possible into the solution to obtain reliable readings. In order to drive this system, I need to use a suitable microcontroller. I've chosen to use Arduino because they're very cheap and easy to use. They don't, however, support threading, and I need to do two jobs, namely controlling temperature and the rotation of the stage. So I've actually designed this system that uses two Arduinos to do these jobs. Up at the top here we've got a simple linear regulator. This is an LM7805, and the idea is that we can feed the entire system 12 volts, which we need for the stepper motors in any case, and this will provide the 5-volt rail for the Arduinos. On the left hand side here we have the Arduino that's responsible for temperature control. Very simply, we have a sense line coming in that comes from the temperature sensors, and then we have a little OLED display so we can see what's going on. Additionally, I always like to have little debugging LEDs, so I've got 3 LEDs connected as well. I've got some headers on the board for temperature sensors. There's actually 3 of these. When I initially started this project, I really wasn't sure if I could just get away with one temperature sensor or whether I'd need to also measure the air temperature or the hot plate temperature itself. So there's 3 headers on the board for that, and then there's an additional header with some additional data lines just in case I wanted to do anything else special as well. On the right hand side here is a second Arduino that's simply configured as a stepper motor driver. It's connected to a DRV8825 stepper motor driver. These are very common off-the-shelf things, easily replaceable if you manage to burn one out. We've got the usual LEDs down at the bottom. There's 3 of these, and the idea is that one will light up when the stage is rotating clockwise, the other will light up when it's paused, and then the other will light up when it rotates anti-clockwise. We've got a couple of little headers on the board here. We've just got auxiliary because, again, when I started this project I wasn't really sure if I needed to do anything else, and I have a little header here that we can configure micro stepping with as well. So this is the overall PCB design for the Rotary Crystallizer. I do like some kind of symmetry in my design, so I've got one Arduino and all of its stuff on one side, and then the other Arduino and all of its stuff on the other. It looks really quite nice. On the left we've got the temperature controller, the OLED display, its 3 output LEDs, and we've got the inputs from the temperature sensor plus some auxiliaries as well. On the right hand side here we've got the motor control Arduino and its corresponding 3 LEDs, the stepper motor driver, the header for the micro stepping, and then an auxiliary pin header again if we need it. Just fair warning, if you intend to send this design off to a manufacturer and have it made, that there seems to be some inconsistency with hole patterns between manufacturers of these OLED displays. It turns out that the hole pattern in this design doesn't actually exactly match the hole pattern that I have in my own OLED display. I think in future revisions of this PCB I'll actually remove the drill holes and just suggest that the OLED display is held in place with double-sided foam tape. This is the overall 3D design of the circuit board. Looks really nice. Absolutely fantastic. This is a good point to mention my sponsor for this video, JLC PCB, who created the PCBs for this project. JLC PCB can produce multi-layer PCBs and offer a wide choice of PCB and silkscreen color and very low cost and fast delivery times. They can also produce PCBs on flex material and even aluminium if your project requires it. JLC PCB also offers an SMD assembly service, so if you provide them with a bill of materials along with the Gerber, they can handle the manufacturing of your project for you, which is especially great for projects using small components. This is especially streamlined if you use Easy EDA and pick their one-click ordering service. One-click order is very straightforward. We just go to Fabrication, one-click order. We'll do a quick design rule check, and then we're ready to place the order. Once you've uploaded the files, you can do some additional configuration. For my project, I wanted the PCBs to be black. These are the finished PCBs. I think they've turned out really very nice indeed. Very nice finish on them and excellent quality. So this is the fully assembled PCB mounted in the case. I've mounted it on a piece of aluminium plate and it sits behind the glass window at the front of the case so you can see it all the time, which is very nice. On the right hand side here, we have a toggle switch which turns the motor on and off. And then on the left hand side here, we've got 2 toggle switches that control which mode the temperature controller is in. So if I flick them both up, it will go into overheat, which will drive up the temperature of the solution to 70 degrees and keep it there. If I flick that switch down, we end up in preheat, which will allow the temperature to drop back down to 54 degrees, ready for planting my seed crystal. And then if I flick the other switch up, it'll go into temperature control mode. Currently it says phase 4 because it thinks that the cycle is finished, but if the temperature was high enough, it would start at starting and then phase 1, phase 2, phase 3, phase 4. Obviously, to run this system, we need some code for the Arduinos, and I've uploaded all of the code onto GitHub for you. There's a few bits and pieces in here. We've got temp controller, which is a temperature controller Arduino, and we've got the rotator and then some additional stuff that I'll talk about in just a moment. This is the stepper motor driver software to rotate the stage inside the crystallizer. There's nothing very special in here. That's all it does is rotate the stage. The way it works is it'll rotate the stage in one direction for a set period of time, pause, and then it'll rotate the stage back for another set period of time, and then pause, and then just repeat over and over. This actually uses the Accel stepper library, so you'll need to install that in the Arduino IDE before compiling and uploading this code to the Arduino. The reason I'm using Accel stepper is I don't want the stepper motor to suddenly turn on and jerk the stage. If that happens, it might cause the crystal to become unmounted, and that would be bad. So we use Accel stepper just to gradually increase speed and gradually decrease speed so nothing strange happens. But yeah, that's all there is to it. Very simply inside the loop here, we can see that we're rotating in one direction, we rest, and then we rotate back to where we started, rest, and then just loop over and over. This is the code for the temperature controller. As before, this makes use of additional libraries, so you'd have to make sure that all of these are installed in the Arduino IDE before you compile and upload this. There's several libraries in here. We've got OneWire and Dallas Temperature, which are both required for the temperature sensor. We've got SPI and Wire and Adafruit GFX and Adafruit SSD 1306 for the OLED display. So yeah, it's quite heavy on libraries. This block of code here is a bitmap to display when the system starts. I thought since I'm using an OLED display, I might as well have some fun with it, so it displays my logo on startup. There's a fair amount of comments in this code that may help you find your way around, or it may help you get entirely lost. I'm not entirely sure. There's been quite a number of changes while I've been developing this stuff. So there's a whole bunch of comments up at the top here which are merely a collection of milliseconds. So this is how many milliseconds that there are in 120 minutes, for example, and this is how many milliseconds there are in 30 minutes. And all of this was done ahead of time so I could program in essentially a cooling curve for this system. But I've left these in case I want to change them or anybody else wants to change them. It's quite a useful reference. Underneath all of this is the initial setup. So the temperature change that I'm going to apply is 0.0625 degrees, which is the smallest temperature change we can actually get out of the temperature sensor. And then we've got the initial start temperature of 47. And then underneath this are the phases. So this is the phases that the system goes through. So this one here, phase 1, says it changes the temperature every 51.4 minutes, which works out at 1.75 degrees per day, for example. And then there's another phase underneath that will change the temperature every 2 hours, or 0.75 degrees a day, every 1 hours, every 45 minutes, and so on. And there's various little comments on the end to which tests these actually related to, but I'll get into all of the stuff about the cooling curve later on. We've just got some additional configuration up here for which pin drives the heater and which pins drive the switches. We've got start temperature, target temperature, and so on, and some little bits and pieces for display. This is the main loop of the program. I'll just go over the main points real quick. It's kind of messy in here, and I think this would benefit from a little bit of refactoring and a tidy up. But in short, every time this loop runs, it will go and get the value from the temperature sensor, and then it will make some decisions depending on what the status of the panel switches are. So for example, if both switches are off in the down position, the machine is off and it's doing nothing, it just sits there idle. If panel 1 switch is low and panel 2 switch is high, the machine is in its preheat status. So what this will do is it will drive the temperature up to 54 degrees and just hold it there. If both switches are high, this is actually the overheat phase. So this will just drive up the temperature to 70 degrees and hold it there. This section of the code is responsible for the slow cooling curve itself. So if panel 1 switch is high and panel 2 switch is low, we're in the slow cooling regime. And then down at the bottom here on lines 196 through 211, this is actually where all the decisions are made about how fast to cool the system. So if the target temperature is greater than 44.5 degrees, we're in phase 1 and we'll use phase 1's cooling. And if the temperature is greater than 43, we're in phase 2, so we'll use phase 2's cooling speed. And if target temperature is above 40, we'll use phase 3's cooling speed, and so on. So that's all that part does. I think there's probably a more efficient way of doing this. Again, this has all been highly experimental, and it's just been a bunch of time figuring things out and why things work the way they work. I think in the end it might be more appropriate to basically just load in a file and have the system read that. So just a file of values, for example, where we could say, well, look, for the first 24 hours, this is how fast I want to cool the system, and for the next 12 hours, this is how fast I want to cool the system, and so on. Down at the bottom is the hot plate controller. Since this is just controlled with a relay, there's no PWM available for these hot plates. PID seems a little bit like overkill, so I'm just using bang bang control in here. I am aware that there's a library out there for Arduino that uses like a strange, like slow PWM, if you will, that will just continuously turn the relay on and off depending on PI and D values. But yeah, it did feel like it was perhaps a little bit too much for this. So yeah, it's just simple on-off control down here, nothing special. Down at the bottom here, we have a section of code that sends data over serial. It's very useful in systems like this to have some kind of record of what's occurred during an experimental run, and so it does exactly that. It will just print out the status message, which is basically what phase are we in. It'll print out the target temperature, and it will print out the current temperature. And we can use a computer at the other end to go and log all of this data to a file, and then we can open it up with graphing programs and stuff and see what's going on in there. To that end, I've got a program here written in Python that runs on my Linux computer that's hooked up to the Arduino. Just opens up the serial port, listens for data coming in, and every 20 rows or so of data that comes in, it will just go and log them to a CSV file so I can analyze them later. To accompany that program, I've written another program in Python that will read in the CSV file and plot out the data. If I just scoot down to the bottom real quick, we can see where the plotting happens. The first plot will plot out the full temperature data, and it uses matplotlib to do this, so we can zoom in as well, which is really, really nice. And then down at the bottom, we can actually plot out the error data as well. Since we're getting the target temperature and the actual temperature over serial, what we can do is just work out the difference between those things and then plot the error over time, which is also very, very handy in debugging a system like this. Before getting started, we need to know some things about solubility. The literature is really good, but it mostly misses any kind of real recipe, as it were, that documents the required weights and volumes. The assumption probably is that the reader knows something about growing crystals. Here's a solubility curve for potassium dihydrogen phosphate, and we can see on it that the solubility increases with temperature. Because my beaker is 500 ml, I've created this graph showing how many grams of potassium dihydrogen phosphate will dissolve in 450 ml of water without the final volume ending up too high. Because I need a 20-degree overheat without evaporating too much of the solution, I chose a start temperature of almost 48 degrees, which requires 176.5 grams of potassium dihydrogen phosphate. Assuming a temperature drop of about 10 degrees over the growth cycle, I should be able to grow a crystal of at least 31 grams. The initial start temperature will actually be 47 degrees, which will ensure an initial supersaturation of about 1.5%. Over the first 36 hours, the temperature will drop to 44.5 C. At this stage, the solution will be supersaturated by about 7%. The solution will be metastable at this point, which is to say it's very unstable. Sudden disturbances may cause it to crash out and suddenly precipitate all of the excess potassium dihydrogen phosphate. So I can't keep cooling at this rate either, so the cooling rate needs to be carefully controlled from here on out. After a huge amount of experimentation, I ended up with this cooling curve. You can see the initial drop to 47 C and then a gentle slide over the next 34 hours to 44.5 degrees. The cooling rate is then throttled back to 0.75 degrees per day for the next couple of days. After about 2 days, the crystals gained enough mass and surface area that the cooling rate can be increased again. This graph is the culmination of a year's worth of experimental work. Unfortunately, it can take days for an error to become apparent in a system like this, so if you intend to replicate this, record what you do and learn from the errors. The growing solution is prepared by adding 450 ml of water to a beaker. Tap water is no good for this as it contains far too many impurities. I actually use deionized water for this because it's cheap and relatively pure. Distilled water might be better. 176.5 grams of potassium dihydrogen phosphate is added, which will yield a slightly supersaturated solution at 47 C. The potassium dihydrogen phosphate I use is common aquarium grade. I found that food grade tends to be quite poor and yields milky solutions, whereas aquarium grade doesn't. I guess that fish aficionados are really quite particular about the grade of stuff that they use. 0.5 grams of EDTA is also added. This is a chelating agent that will mop up any heavy metal ions that have made their way into the solution. I heat this in the microwave for a couple of minutes to about 50 C or so, and then drop in the stir bar, mount it on the hot plate along with the lid and the temperature sensor, and start the overheat cycle. This will raise the temperature to about 70 degrees C and maintain it. Once the KDP has been fully dissolved and the temperature has reached 70 degrees, the solution is filtered to remove any particles of dust and detritus. For this, I use a 2.5 micron filter in a Buchner funnel. Smaller filters would be better, but I have to do this step really fast. The filter and the flask are both preheated by running boiling water through it first. If this isn't done, the temperature of the solution will actually drop low enough to start crystallizing out, which clogs the filter and we lose material. The beaker is returned to the crystallizer and allowed to continue the overheat cycle for 24 hours. The overheat cycle is necessary to end up with a very stable, supersaturated solution. Once 24 hours has elapsed, the switch is flipped to preheat and this will drop the solution down to 54 C, ready for planting the seed crystal. To grow a seed crystal, we need a suitable point seed. These are grown rather haphazardly by just dissolving KDP in hot water until no more will dissolve and just letting it cool overnight. By morning, the bottom of the beaker is covered in crystals and the clearest and most well-formed crystals are just snapped off. For this crystallizer, I only need the tips. A little prep needs to be done with the seeds. First, the base is cut square, and I just do this with a pair of small wire cutters since the crystals are small enough. The bases are then filed flat and square with a small file. Once this is done, a small hole is drilled into the center of the base. This is done to ensure that the adhesive actually has something to properly key into. If not, you may find that solution works its way in between the layer of adhesive and you lose the crystal. For gluing, I use Loctite cyanoacrylate superglue. I've tried many other kinds of instant glues, such as UV curable adhesive and other brands of superglues, and these all seem to result in either the crystal cracking, as in the case of UV glues, or a white bloom on the surfaces of the crystal in the case of other superglues. The small drill hole is filled with glue first, and then the rest of the base is carefully painted with glue. I make up a few of these at a time. Before I think about mounting the crystals, the platform assembly is placed in a beaker of water at 60 C. The purpose of this step is actually to make sure that the platform is at the same temperature as the solution. The solution is highly saturated at 54C and at 47C is fully saturated. Dropping in a cold platform will at least locally drop the temperature to the point where spontaneous crystallization will occur. To mount the seed, the preheated platform is pulled out and water wiped off the surface. A spot of glue is dropped in the central divot and the crystal mounted in it nice and square and gently pressed down. This will actually cure pretty quickly. Once this is done, the entire assembly is dunked back in the water to bring it back up to temperature. This is done with a series of short dunkings to allow the crystal to warm up gradually to avoid cracking it. The surface of the crystal will actually dissolve slightly during the dunking process, but this is really desirable since it will remove dust, fingerprints and any microcrystals from the surface. The platform is left in the water while the temperature sensor and lid are removed from the crystallizer and the platform transferred to it. The growth cycle is now initiated. This simply switches off the heater until the start temperature of 47C is reached. During this time, the crystal will continue to dissolve a little, but again, this helps the process by removing surface impurities and imperfections. Once 47C is reached, phase 1 begins. This slowly cools the solution from 47C to 44.5C at a rate of 1.75 degrees for every 24 hours. Anything under 47C is supersaturated, so we need to gently cool at a rate that doesn't upset the solution but still reaches the target temperature in a reasonable amount of time. An initial rate as high as 3 degrees in every 24 hours is possible, but the stars really have to be aligned for that to work out. By the time this first phase is done, the crystal surface has regenerated and should have nice clearly defined edges and has grown significantly, already quicker than by evaporation. The supersaturation level is about 7% and phase 2 begins. Phase 2 continues cooling at a rate of 0.75 degrees per day for the next 2 days. This ensures that the solution remains in a supersaturated state for the duration of the growth. Since the crystal is increasing in size and surface area, we need to increase the cooling rate as the growth continues. So phase 3 runs at 1.5 degrees per day and phase 4 runs at 2 degrees per day. I mentioned previously that PID is not actually implemented on the controller. With the machine running in room temperature, the system is remarkably stable. The controller logs data continuously back to a laptop, and if I notice any slight oscillation, I can just tweak the heater knob. This is my proportional control. This rarely happens. I look maybe once or twice a day and tweak it every day or so. As we can see in this error chart, the total error doesn't exceed 0.0625 degrees over the course of hours and days of running. If all goes well, after just a few days, we have a beautiful, perfect crystal. Look at this. This is absolutely spectacular. This is way cool, but I figured it would be way cooler to set up a webcam inside the case and to do a time lapse. Look at these. These are absolutely fantastic. Here's a view from a different angle. Once again, absolutely beautiful. Once the temperature gets down into the high 30s, we're ready to pull the crystal out. At under 40C, condensation at the top of the beaker is no longer enough to keep the walls wet. If they dry out, microcrystals can form, causing a sudden crash. To remove the crystal, I remove the platform and just pop the crystal off. It's just held on with a small spot of glue and intermolecular forces. I immediately wrap it up in lab-grade tissue to allow it to dry and cool slowly. I normally just keep it in my closed hands for a few minutes and then leave it on the worktop for a while. And this is the final result. This is absolutely spectacular. Beautiful, optically clear crystals. I've grown several of these quite successfully now and I'm getting quite a collection. For optical uses, I'll need to cut and polish these, but this is a topic for a future video. It's been a long road from many early failures and I've learned an awful lot, but now I have a fairly reliable system and the results speak for themselves. As it stands, the system is as stable as it can be without significantly increasing complexity. Failures can and do happen, so you have to watch out for those. Impurities and dust can still get in during seed planting and can cause the crystal to crack at any stage in the growth cycle. Even hairline cracks will release microcrystals into the highly saturated solution, which will cause the solution to suddenly crash out, turning this thing into a very expensive snow globe. Sometimes a crystal will start twinning, which also causes stress cracks. There's no point crossing your fingers and hoping it fixes itself. It never will. Be prepared to have to do it over and be prepared to experiment. I don't think it would be too hard to scale this up to 1 litre with the existing setup, resulting in larger crystals, but for now, this will do just fine. As always, a huge thank you to my awesome Patreons, donators and subscribers. Your support makes science and engineering videos like this possible.